Hi, I'm Tristan Mamerto, and this is my presentation for Physics 231. This will be about the physics of music. Now, first off, why did I pick it? I've always been interested in music. My family had a lot of singers in it, and I took piano and guitar lessons before, but I always loved the electric bass, and Flea from the Red Hot Chili Peppers is one of my biggest influences. I thought this project would be a great way for me to, well, not only learn about the music, but appreciate the meaning and the physics behind it. One can't discuss any music without, well, discussing waves first. There are multiple types of waves, but here are two of them: transverse and longitudinal. Transverse waves propagate in a perpendicular direction than their displacement, or they move up and down. See this tip? It moves up and down while it propagates or moves in the other direction, while longitudinal waves propagate in a parallel direction to their displacement. So they displace in this direction while the wave travels in that same direction. Why are those waves important? Well, longitudinal waves are actually what create sound. Well, what is sound? Sound essentially comes from vibrations through a medium like air, but it could also go through liquids or solids. But sound is a combination of compression and rarefactions of the air molecules, as shown here. They're due to differences in pressure. Where there's low pressure, air molecules tend to equilibrate, and they try to fill in those gaps, which leaves another low pressure point, which it compensates for, and this just repeats over and over. And that creates vibrations, which our eardrums interpret as sound. So now that we know what sound is, what causes the variations of sounds? Oh, first thing we're going to go through is volume. So since sound is a wave, does the volume knob on the amp, does it change the wavelength or the frequency? Well, neither, actually. The volume is changed due to the amplitude of the sound waves. Intensity is defined as power per unit area, and it relates to sound waves because sound waves can carry energy. Because of this relationship, we define that the intensity is proportional to the amplitude of the wave squared. Here it is, that relation. Just a quick example of this is, why does an acoustic guitar have a hole right here? Well, it uses that idea between volume, intensity, and amplitude. By itself, a string's vibrations doesn't create much sound. It's not very loud, so it needs something in order to make it louder. An acoustic guitar utilizes the fundamentals of sound to increase the intensity of the wave. The opening of the guitar's body, right here, it allows sound to come in, it bounces off the walls, and comes out of a small concentrated opening. All of the sound waves add together and create a greater amplitude, which creates a greater intensity, which then creates a greater volume. Okay, so now that volume is explained, we can get to the structure of a standing wave. So wait, what is a standing wave? Well, it can be thought of as two transverse waves, here and here, you can see, two transverse waves that have the exact same frequency, wavelength, and amplitude, but they're traveling in opposite directions. These waves combine due to the principle of superposition, which posits that two waves that are simultaneously at the same place at the same time will add their displacements together. So here, this wave is a combination of these two. So arising from these are things called nodes and antinodes. So here, these red dots right here, these are called nodes because their amplitudes sum to 0. And antinodes are just the opposite. They're the ones that create the maximum amplitude that you see there. We can easily see that standing waves can also be represented as having both ends fixed in place, so we can derive an equation based upon that fact that the nodes must be in those specific positions. Converting those special wavelengths to frequencies, the specific frequencies are known as harmonics. Now we can apply this knowledge to understand why an instrument is created the way it is. We can see the equation of the fundamental frequency of a vibrating string. It's closely emulated by a guitar or bass string, which is fixed at both ends by the bridge and the nut of the guitar. And when a string is hit with a disturbance, like a pick or a pluck, it causes the string to vibrate at the fundamental frequency of the string. First, we have the string's linear density, which is shown right here, or the mass per unit length. We can see that the density is inversely proportional to the frequency. So that means that the thicker, fatter strings have a lower pitch, while a skinny wire-like string would have a higher pitch, which explains why a bass's low E string up here sounds a lot different than a guitar's high E string, which is down here, super thin. The frequency also has to do with the tension of the string. It can be changed using the tuning pegs of the guitar. Twisting it one way creates a tighter string, and then twisting it the other way loosens it. The more tight and tense the string is, the higher the pitch, because you can see it's directly proportional. And twisting it the other way, loosening it, would lower the pitch. Last thing here is the string's length. So the shorter the string, the higher the pitch. This is emulated by the fretting of the guitar bass. Those metal bars that you can see here, or the frets on the neck, they serve a great purpose. They become the new nut of the string. When they're pressed down like this and plucked, the string is effectively shortened, which directly affects the frequency, and it becomes a higher note. There are two other qualities of sound that I'll go over that are affected by physics. So, how come on a piano, for instance, if you play a C, it sounds a lot different than a C that is sung by a choir man, or a C blown through an oboe? So what causes that difference if they're supposedly the same note? This is due to the sound quality of the note, what's known as the timbre. Something like a tuning fork would vibrate like a simple harmonic oscillator, and it produces a pretty sinusoidal wave. However, for things like an oboe, the sound is created by a much more complex process, and due to the superposition of all the waves coming together, the oboe produces the same frequency as a C on a tuning fork, for example. However, the waves appear a lot different due to the complex arrangement, as you can see here. This causes a difference in how the note sounds. Well, another phenomena that puzzled me were octaves. So I understand that, well, different frequencies create different pitches. So how could a low B string sound the same as a high B if they're completely different frequencies? Well, it turns out because they're related. Octaves are simply the double of the fundamental frequency of the first octave. So, for example, if the original frequency was, say, 130 hertz, so say this is 130 hertz frequency, an octave would be twice that value. So that would be 260 hertz here, and so on. That's it. This is a lot of fun to make. All right, thanks.